Hello everybody, and welcome to this Copernicus Marine Service training about the Arctic region. My name is Etienne Sayuk from Noveltis, and today I'm going to show you how to compute sea ice extent anomaly and sea ice thickness evolution in QGIS software. The Arctic covers a vast area, most of it being uninhabited. As the region is warming up twice as fast as the rest of the world, it requires a more intense monitoring. Models also need reliable observation as inputs to provide the most accurate estimations. This is where space-based technologies have a key role to play. They constitute a powerful tool to observe this particularly remote area on a daily basis. For example, satellite recordings show that the sea ice extent in the Arctic changes seasonally and annually. The sea ice extent is defined as the total area in which ice concentration is at least 15%. Every year, the minimum extent of Arctic sea ice is reached in September, and this minimum has been plummeting for the past decades. The Ocean States Report Summary and the United States National Snow and Ice Data Center highlight the dramatic decline of the Arctic sea ice extent in September in the figure here. In this context, the operational, precise and reliable Copernicus Marine Service products for the Arctic are a great asset to analyze and forecast the sea ice condition in the region and assess in near real time the state of the sea ice layer. One way of carrying analysis and get the maximum out of the Copernicus Marine System products is to exploit them in a GIS software. This tutorial aims at demonstrating the processing of the Copernicus Marine Service products for the Arctic in the QGIS software with the NetCDF2 GIS plugin developed by Noveltis. This plugin helps you to easily compute some operation between layers with the Copernicus Marine Service products. First of all, I invite you to create a new project in QGIS, and we are going to open the Copernicus Marine Service plugin by clicking on the logo here to open the plugin. Once it is done, you can just reduce this window. And now we are going first of all to change the projection of our main project in QGIS. We are dealing with polar products in the Arctic, so we are going to select a stereographic projection. To do so, right click on the PSG panel here, and we are going to change the default projection. Here you can look for North Pole stereographic projection here and select it. Once it is done, you can click on apply and OK. Now we are going to add a background layer to add some contextual information to our exercise. Here you can click on layer, add layer, and we are going to open the add WMS layer panel. You just have here to connect to the map server demo, and all the information of this connection and all the data needed for this exercise are available on the user manual provided on the Copernicus Marine Service user platform. Here select the map server demo and connect. We are going to use the blue marble layer, but we are going to choose to project it on a special projection, which is the Canada Atlas Lambert projection. So here you are going to select the coordinate reference system, and here browse, and you can select the Canada Atlas Lambert NAD 83 here. Once it is done, you can click on OK, and here add. So it's going to pop with a window of select transformation, and you are going to select the first transformation here. Click on OK, and then you can close this window. As you can see, the map is stretched and you can see the world from the North Pole centered in Canada. So you can zoom on your map here and discard the warning here. Here you can see that the general projection of the project have been changed to the Canada Lambert one of the blue marble layer, but we want for our project a North Pole stereographic projection. So go back to this panel and set back the North Pole stereographic projection. Click on apply and OK. It should take some time to load, but after you have a North Polar stereographic projection centered on the Greenwich meridian. Once it is done, we are going to import sea ice concentration data from the Copernicus Marine Service product and compute climatology between the months of September 1993 and September 2010. To do so, open again the window of the NetCDF QGIS plugin and import the NetCDF file containing your data. Here we can import the data of September 1993 to 2010 and the layer, the NetCDF file containing the data for the months of September 2020. So the first one and the second one. So here you have access to the name of your file, the path, and several information on the variables contained in your NetCDF file and metadata. This product is a multi-year reanalysis on the Arctic based on a physical model from the Copernicus Marine Service that assimilates sea ice concentration and thickness from the CMEMS sea ice observations. The spatial resolution is 12.5 kilometers, and you can download it on a daily or monthly mean. Here we have downloaded it on a monthly mean from 1993 to 2010, and we have downloaded sea ice concentration and sea ice thickness variables. What you can do now is just add layers of sea ice concentration to your main project. To do so, select the first file here, and first of all we are going to compute sea ice concentration climatology on this period. Right click on the sea ice concentration variable here, select add layers, and on the window select all the months of September from 1993 to 2010. To do so, you can click Ctrl on your keyboard, press Ctrl on your keyboard, sorry, and click on all the months of September. Using the Shift key, you could have selected all the layers for each month, but here we are focusing on September sea ice extents. And here we are. Here you can just change the group name to sea ice cons 1993 to 2010. And here you can click on add and close. All these layers corresponding to the months of September during the period have been added to the layer panel here in QGIS, but if you reduce this window you cannot see them on your project. That is because they have a special projection which is not the one of our main project. So we are going to create in QGIS a CRS corresponding to the projection of all these layers and then apply it to them. To do so, we can go back to the the plugin and to the metadata, and here you have some informations on the projection of your Copernicus Marine Service product. So copy this projection information, go back to the QGIS project, select settings and custom projections. Here we are going to create a new projection. So to do so, you can just, here I have already created it, but I'm going to delete it and show you again how to do. So here click on the plus icon and change the name of your new projection, CRS. We are going to call it Arctic Stereo. And here just we are going to set a ProString format in order to just paste the projection contained in the metadata of our Copernicus Marine Service products. Here you can paste the projection of the metadata, and we are just going to change here the K coefficient and just 0.00001. Here you can click on validate to see if your projection definition is valid. It's okay, and then click on OK. Now we are just going to select, for example, all our sea ice concentration layers, right click on it, go to layer CRS, and here we are going to set the layer CRS. We need to find the user defined coordinate system and select the Arctic Stereo here. Click on OK, and here you can see that your layer is appearing on your project. So now we can see the evolution of the sea ice concentration on the months of September between 1993 and 2010. After that, we are going to compute climatology, which is a mean of the months of September between these 2 years. To do so, we are going to open the raster panel raster calculator here and type the expression provided in the user manual that you can download on the Copernicus Marine Service platform, or you can just select each layer one by one, double click on it, add the plus sign, and then divide by the number of layers. We are just computing here a simple average computation. You just have to change the output name here, and we are going to select climatology between 1993 and 2010. Okay, I'm going to save it and click on OK. So here the resulting layer is appearing, and we are just going to drag it on top of all the other layers. This new layer is in levels of gray, and first of all we are going, before changing its appearance with colors, we are going to change the range of values from 0 to 1 to 0 to 100 by multiplying each value by 100 in order to apply some filters later in this exercise. So here we are going to again open the raster calculator, select the climatology layer here, and just multiply it by 100. Oops, sorry. Here we are going to change the output layer to climatology 1993 2010 underscore 100 and click on OK. Once it is done, we are going to quickly change the style of this resulting layer. To do so, we are going to right click on it, open the properties, and here we are first of all changing the render type from level of gray to single band to the color, setting the minimum value to 0 and the maximum one to 100, and just here invert the color ramp to have blue values as minimum values and red color for maximum values. Click on apply and OK. So here you have a representation of the climatology of sea ice concentration between 1993 and 2010. Now to compute sea ice extent, we need to filter this layer and select only sea ice concentration higher than 15%. To do this operation, it's easier to deal with polygons, so we are going to convert this raster layer from a .netcdf file to a polygon layer on a vector format. So click on raster, conversion, and select polygonize. Here the input layer is a climatology 1993-2010 _100. We are going to create a field which is sea ice concentration, and we are just going to give a name to the resulting layer and save it to a file, and we are going to call it climatology the period _ polygon. Here I'm just going to save it again, and you can click on run. Once it is done, you can close this window. Here you cannot see this vector layer already, but we just have to change the CRS and go to layer CRS and select the user CRS we have created, which is the Arctic stereo one. Now you have here the polygons of each sea ice concentration between 0 and 100 on the months of September between 1993 and 2010. We are going to apply a filter on these polygons to only keep polygons with value higher than 15%. So right click on this polygon layer and select filter, and just type the expression sea ice concentration higher or equal to 15 and click on OK. You can see that the resulting extent is in orange polygons here all over the Arctic region. Now we are going to apply just a simple correction on geometries and polygons of this layer between merging them all to have only one area of sea ice extent, of sea ice concentration higher than 15%. To do so, we are going to open the processing toolbox, and here we are going to look for fix geometries function. Open it and apply it to your layer climatology polygon. You can save the resulting layer as climatology polygon fixed. Now run this function and close this window. Again, change the layer CRS to the Arctic Stereo 1, so you can select it here, or you can go to set layer CRS and select Arctic Stereo here. And now finally we have a layer, the climatology layer, made of polygon fixed, so we can merge them all together. And to do so, we are going just to use the vector geoprocessing tools here and select the dissolve option, which allow you to merge all your polygons together. So we are going to select as input layer the climatology polygon fixed layer, click on run and close this panel. Here you can see that you have only one polygon remaining here in purple, and this is the mean sea ice extent for the months of September between 1993 and 2010. The last step of this first part is to compute the area of this sea ice extent in squared kilometers. So here you can just rename this layer, right click on it and select rename, and select, for example, climatology underscore the period and underscore sea ice extent. If you go on this layer, right click on it and open attribute table. Here you can just toggle to editing mode, and we are going to compute the area of this polygon. Here you just have to open the field calculator, select the new the output field name to area in kilometers, and here the expression will be area, the existing area, and multiply it by 10 exponent 6. Minus 6, sorry. Click on OK, and here you have the area of this polygon of sea ice extent climatology between 1993 and 2010, which is equal to almost 7 million of square kilometers. Now we are going to do, you can just close the editing mode and save the modification you have done on this layer. Now we are going to do the same methodology on the layer corresponding to the month of September 2020, and compare the sea ice extents between these two layers, the climatology and the 2020 layer. To do so, we are going back to the netcdf QGIS plugin here, and we are going to select the file containing the month of September for the year 2020. We are here going to use another method to filter sea ice concentration higher than 15%, but you also can apply the same methodology as before. First of all, go to variables and select the sea ice concentration variable of this netcdf file. Right click on it and select add layers. Here we are going to import only one time step. You can change the group name to sea ice concentration 2020. Click on add and close. Reduce the netcdf QGIS panel. Here we need to change the layer CRS of this layer to the Arctic Stereo 1 we have created at the beginning of the training to see the layer on top. we are just going to uncheck all the layers below the one of the climatology period. Now what we can do to filter the sea ice extent, so the sea ice concentration higher than 15%, we can directly select the raster and raster calculator and apply a filter on the sea ice concentration layer for the month of September 2020. So the expression is this one that you can find on the user manual, or just type with the layers and the computational signs here. The output layer here need to be changed to sea ice concentration, sea ice extent 2020 .tif. Don't need to give the extension here. Select the output format to GeoTIFF and then click on OK. Open the raster calculator here and just apply a filter on this sea ice concentration corresponding to the month of September 2020, and we are going to apply a sea ice concentration layer higher than 15%. Just save it to your working directory as sea ice extent 2020, for example, and then you can click on OK to make the calculation. So here you have a resulting layer with only 0 and 1 values. The value 1 corresponds to concentrations, sea ice concentration higher than 15%. So values counting for the sea ice extent, and the 0 values are corresponding to concentration below this threshold of 15%. Now we are going to convert this raster layer to the polygon format. So select raster, conversion and polygonize. We are going to select the sea ice extent 2020 as the input layer and change the field to create to sea ice concentrations. Again, we are going to give an output name and save it to file. For example, sea ice extent 2020 polygon .shapefile. And I'm going to replace the existing file on my directory. Now you can just click on run on this function and then close. Again, we need to change the layer CRS to show it in our project. Okay. So here, if we go to the attribute table, we have only 0 and 1 values. For polygons with concentration higher than 50%, 1 values, and below this threshold for 0 values. Now we are going to filter this resulting polygon and keep only values equal to 1. So sea ice concentration raster layer with values higher than 15%. That count for the sea ice extent. Right click on this resulting layer, select filter, and here we are just going to select sea ice concentration higher or equal to 1. click on OK. So as you can see, this resulting polygon is the pink one here. Now we are just going to merge all the geometries of this resulting polygon, and we are going to select the vector geoprocessing tool, dissolve again, on the CIS extent 2020 polygon, and we can change the resulting layer and select the CIS extent on 2020 polygon merged. Save and click on run. Close. You need again to reproject it, changing the layer CRS. And here we have the CIS extent during the month of September 2020. Now we can first of all compare visually this extent to the one of the climatology. So if you deactivate this layer here and only consider the CIS extent 2020 polygon merged and compare it with the climatology CIS extent here, you can see that the CIS extent is really low in 2020 in comparison with the climatology between 1993 and 2010. Now we have seen that during this period, the climatology, the mean CIS extent in September was almost 7 millions of square kilometers. So we are going to compute the area in square kilometers for the year 2020. Right click on it, on the layer, open the attribute table, toggle to editing mode here, open the field calculator, and then we are going to name the resulting output to area underscore kilometers, and we are going to multiply the area variable by 10 exponent minus 6 to convert it to squared kilometers. Now you can see that the resulting extent of CIS during the month of September 2020 has been reduced to almost 4 millions of kilometers, which is approximately the half of what it has been during the 1993-2010 period. So this was an interesting exercise to see how physical models from the Copernicus Marine Service assimilating CIS observation can give tools and useful information to see how the CIS conditions evolves in the past decades. Now you can just change and close the editing mode now and save the modifications. Now we have seen how to deal with CIS concentration, and the second part of this training is on CIS thickness. We are going to import CIS thickness between 1993 and 2010, and to see how to extract the time series on some particular sample points, and then how to extract them to another format, the comma separated value format, to apply some transformation or analysis with other softwares as QGIS. So in this second part of the training, we are not using the CMEMS2 NetCDF plugins, but we are going to load the data on a normal way in QGIS and import just a raster layer in order to have all the time steps of our project in only one layer, and then we can compute time series extractions. So first of all, we are going to select raster, layer, add layer, and add raster layer. And here you can browse to the data directory, select the file containing CI thickness between September 1993 and September 2010 and open it. Here you can click on add and just select the CI thickness variable here. Click on OK. It has been added to your project here, as you can see, and now close this window. What you can see is that the layer has not been added to your project. So again, what you can do is just change the layer CRS and select the Arctic Stereo 1. Here you can see that your CI thickness layer have been added to your QGIS map. First of all, we are going to rename this layer with an easier name. So right click on it and rename layer, and we are going to call it CI thickness and just precise the period 1993 2010. Once it is done, we are going to change the style and the render of this layer. Right click on it, open properties, and here we are going to use a single band pseudocolor render type. We are going to, for this step, only show the first time frame of our NetCDF file corresponding to the month of September 1993. We are going to use a minimum value of 3 meters, of 0 meters, and a maximum value of CI thickness of 3 meters. Just remind to invert the color ramp to have blue color for the minimum values and red color to maximum one. Apply and OK. So you can see that the maximum thicknesses of CIs for the first time frame of this layer are in the Canadian archipelago and at the north of Greenland here. What we can do now is extract some CI thickness time series on several sample points. So to do so, we are going to create a new layer to define our sample points. To do so, click on layer, create layer, and we are going to create a new shapefile layer. Here we want to call it, for example, extract points, save it, and here you just have to change the geometry type to point. Okay, now you can click on OK, and we need to edit this new shapefile layer to add some points information to it. To do so, just toggle to editing mode, and here we are going to use this function here of the dots to create some dots on this region. What you can do is just set some dots here on the north of Greenland, select the index 0, here 1, here at the center of the Arctic region with the index 2, and here on the Canadian archipelago with the index 3, for example. So here we have a new shapefile layer with 4 points. You can just close the editing mode here by clicking on the pen icon and save the modifications to your shapefile layer extract points. What we can do is to add geometric information to this layer. As you can see, if you open the attribute table, here we have just indexed, and we want to add some longitude and latitude coordinates to this layer. So open the processing toolbox, look for the add geometry attributes function, select the extract point shapefile as input layer, and click on run and close. If you open the resulting added geometric info here and open the attribute table, you can see that we have some x coordinates corresponding to longitude and y coordinates corresponding to latitude added to our initial layer. And now we are going to do the last step, which is sampling the raster layer values of sea ice thickness during this period on these 4 sample points. To do so, we need to use another function of the processing toolbox, which is called sample raster values. So open this function. We are going to extract time series values on this added geometric information as input layer on the raster layer of sea ice thickness during between 1993 and 2010. And you can just change the output file name to extract time series, for example. And here we are going to just change the output prefix to sea ice thickness on our attribute table. It will replace the name of each column to sea ice thickness. Once it is ready, you can click on run and close this window. So as you can see here, we have a resulting layer called extract time series, and if you go to the attribute table of this layer, you have the ID of each point, their coordinates here, x and y, longitude and latitude, and here you have the sea ice thicknesses of each time frame of the period between September 1993 and September 2010. So it could be interesting to export this layer as a comma separated value file with different columns of indexes, long lat, and values of sea ice thickness if you want to exploit them on other softwares as Python, MATLAB, or any other software. So to do so, the last step is to right click on your layer and select export, save feature as, and here you select the format comma separated value here. You can change the file name to, for example, sample points extraction.csv here and save it. If you click on OK, this CSV file have been generated and saved into your working directory. So now you have access to the time series of this netcdf file, sea ice thickness during this period on each of these sample points. So we are now reaching the end of this training. An additional exercise you can do is to follow the steps of the training on the Baltic Sea and draw ship routes according to sea ice thicknesses classes, as we did on the Baltic Sea. So I encourage you to do this additional exercise following the user manual on the training 2 on the Baltic Sea. All these informations are available on the Copernicus Marine Service platform. So in this training you have seen how to use interesting and free products from the Copernicus Marine Service on the Arctic region to monitor the sea ice conditions, sea ice concentrations or sea ice thicknesses, and extract time series on sample points. Thank you for your attention, and see you soon.